Hello. I want to tell you about a programming language. It's a bit eccentric, but it's a great language to learn if you're interested in compilers, because it shares the same interpreter architecture as many mainstream languages, such as Python. For one thing, it doesn't have variables. I can show you. Let's have a stroll. Welcome to the second compilers challenge. In the last challenge, we covered the reverse Polish notation, where arithmetic operators go after their operand. For example, the compound operation 3 plus 4 in parentheses times 5 would instead be written 3, 4 plus 5 times. We saw how we can implement a stack-based machine to evaluate arithmetic operations written this way. Basically, we scan the sequence of tokens from left to right. Whenever we encounter a number, we push it onto the stack. Whenever we encounter an operator, we execute the operation on the top two numbers of the stack. It's a bit like casting a spell. The stack is the place where you place the required ingredients, and the operator is the spell you cast. And when you cast it, the ingredients become the result that you're after. Another way to look at this sequence of tokens is to treat each token as an instruction. And this is more of a CPU analogy. An operator is an instruction to carry out some kind of arithmetic, and a number is simply an instruction to load that number onto the top of the stack. It turns out that you can extend this simple scheme into a general-purpose programming language simply by adding more operators and allow programmers to define their own custom operators or subroutines. Forth is a programming language that does precisely that. Although Forth is not known as a mainstream language, it has enjoyed grassroots support since its inception in the 1970s. Forth was invented by Chuck Moore, and to him, the language was a response to his frustration with existing software tools, which he viewed as a sort of Tower of Babel. The typical compiler architecture has a hierarchical structure like this. Each layer in the hierarchy communicates to their previous layer and their next layer via a specific language designed for that purpose. This means that in order to understand how the entire compiler works, one must understand each of the languages involved and how they relate to each other. Moore came up with an architecture that has only one single layer, dramatically simplifying the construction of the compiler. Forth's simplicity makes it a good starting point for learning the art of compilers. If you have done the first compilers challenge, then you're already halfway there towards implementing an interpreter for Forth. If you haven't yet, it's never too late. We'll build a simple Forth interpreter in upcoming episodes, but if you're going to implement a programming language, you should know that language and have an appreciation for that language. In this episode, I challenge you to write programs in Forth. Forth is probably going to feel a little different from the languages you are used to, but it's not difficult. Think of it like going to an adventure in a foreign land. Take it easy and soak up their unique scenery and culture. In order to get Forth, you can download a version of SwiftForth for your operating system from forth.com. Or you can use the interactive coding environment on replit.com. Replit allows you to use an implementation of Forth called JSForth in your browser without you having to install anything on your own system. Here's how to do it with Replit. First, you need to log into Replit via your Google account, GitHub account, or Facebook account. Once you're logged in, you'll click Create REPL, then search and select Forth, and then click Create REPL. And now you're ready to start coding in Forth. These are the features of Forth I'm going to cover here. After that, I will describe the code challenge and set you off on your adventure. If you'd like to have a book for learning Forth, I highly recommend Starting Forth, which is a PDF you can get on forth.com. I will also link it in the description. In Forth, the concept of the stack is central to the language. Almost every operation works based on the current values of the stack. The reverse Polish notation expressions we've already seen are valid statements in Forth, and they will produce results on the top of the stack. In the JS Forth REPL, the contents of the stack is displayed each time after executing a statement. To print the top item of the stack, you can use the dot operator. You can add the dot operator to the end of a sequence to explicitly print the result. The dot operator is destructive because it removes the result that it prints from the top of the stack. So you can also use it to clear out the stack if there are any unwanted values there. For the purpose of debugging, there's also the .s operator, capital S, which prints the contents of the entire stack without destroying it. On Replit, the REPL already does that for you in its normal operation, but if you're using Swift Forth, which doesn't do that, .s will come in handy. You can also print a character by its ASCII code value using the emit subroutine. You can find the ASCII code value for any character on your keyboard at asciitable.com, which might be handy for writing a Hello World program. It's possible to write text literals, but I'm gonna skip that because who needs them when you have ASCII? We're going Spartan. The CR subroutine can also be useful. It prints a carriage return to the terminal, creating a new line to help you with formatting. Like other languages, Forth allows you to define your own subroutines. A subroutine is defined starting with a colon and ending with a semicolon. The first thing after the colon is the name of the subroutine. Then you write the list of instructions you want executed whenever the subroutine is called. For example, this defines a star subroutine, which prints a asterisk to the screen, as 42 is the ASCII code for an asterisk. Don't forget to put a space after the colon and just before the semicolon at the end. They're important. Let's define it in the REPL. Now, to call it, we simply type star and hit enter. Subroutines do not have parameters. Instead, values are passed to subroutines by putting them on the stack immediately before calling the subroutine. For example, this is the definition for the increment subroutine, which adds 1 to the passed in number. It expects the number to be incremented to have been placed on the stack before it's called. When it is called, it puts 1 on top of the stack, then executes the plus operator. Now when the subroutine exits and the control is returned back to the caller, they will have the result ready for use. To call this routine, a programmer would simply type the number they'd like to increment, followed by increment. Note that a subroutine is called in postfix notation, just like normal operators. Different subroutines may expect a different number of values to be passed to it on the stack. They may also produce a different number of results to be left on the stack when they're done. For example, let's say there's a subroutine called sum3 that sums the top 3 numbers on the stack. To use it, I would first put the 3 numbers I want to sum on the stack, and then I would call sum3. Sum3 would be implemented like this, with 2 plus operators. The first plus to add the first 2 numbers on the stack, and then the second one to add their result to the third number. It is often helpful for users of your subroutines to document what values your subroutine takes from the stack and what values it puts back to the stack. In other words, its inputs and outputs. In Forth, there is a convention of using the following notation. Parentheses in Forth are ignored by the interpreter and considered a comment, so this notation is more for humans than it is for the machine. We have 2 dashes in the middle. The inputs are on the left of the dashes and the outputs are on the right of them. And you can name them as you wish. With the input list, the rightmost input is the one expected to be on the top of the stack. One more thing, don't forget to put a space after the opening parentheses and before the ending parentheses. In some situations, you may wish to manipulate or rearrange the items on the stack in order to prepare it for an upcoming operation. The built-in subroutines dupe, swap, rot, over, and drop do just that. Dupe duplicates the value on the top of the stack. It can be used to implement a square function by first duplicating the value to be squared and then applying the multiply operator. Another situation to use dupe is when you need the same value in multiple steps within a calculation. For example, with this equation. We start with an A on the stack. Then we apply dupe to get two A's on the stack. Now we apply 2 plus to get A plus 2 on top. And then finally apply multiply to get the final answer. If we define a subroutine for this formula, it will look like this. The swap subroutine swaps the top two items on the stack. The rot subroutine rotates the third item from the stack to the top, pushing the top two items down. The drop subroutine removes the top item of the stack. The over subroutine duplicates the second item of the stack and puts it on top. Here's an example to demonstrate the usefulness of these stack manipulation routines. Let's say you want to make a subroutine to calculate this formula. The values A, B, C are provided for you on the stack like this, with A on top initially. How would you do this? Well, in order to square A, we had better make a copy of it. In fact, we need to make two copies of it. Two of them to calculate A squared, but the third one we need to save it off to use to multiply it to B later. So we call dupe twice to get 3 copies of A. Next, we multiply to get the square of A. And now we move on to multiplying A to B. But A and B are not on the top of the stack. So we're going to use rot twice to rotate both of them to the top of the stack to get ready. And now we multiply. Now we have the results of A squared and A times B on the top of the stack, so we can add them together with the plus operator. Next, we want to divide the current result by C, but the divisor operator requires their order be reversed. So we use swap to switch their position, and now we're ready to divide and get the final result. So this is the full sequence of instructions we use to calculate our formula. What a piece of code. In fourth, an if statement cannot be used directly in the REPL, but instead must appear within a subroutine definition. This is an example. Here, we assume OK is a subroutine already defined that prints OK. 20 greater than will determine if the value on the stack is greater than 20, and put a truthy value or a falsy value on the stack. Fourth treats any non-zero value as truthy and 0 as falsy. Why they decided to use -1 as the truth value by default, I'm not sure about that. Then we encounter the if operator, which will execute the sequence coming after it, but before the then, if the result was truthy. The if statement in fourth may look a bit awkward. Consider that it is in reverse Polish notation, so the condition goes before the if, and the part that precedes the then is the consequent action. If we add in the else clause, then we have an added alternate action that goes between else and then. Similarly to if statements, a loop must appear within a subroutine definition. This subroutine calls the hello routine 5 times. it creates a counter internally and initializes it to 0. Then it increments it until it reaches 5. So the two numbers you put on the stack before calling the do loop are the starting and ending values for the counter in reverse order. The sequence of instructions between do and loop are repeated for each iteration. If you want to access the counter value, you can use the symbol I anywhere between do and loop, and it will put I on the stack. Let's print out I using the dot operator. Here you can see that the starting value 0 is included, but the ending value of 5 is not. Because do loop is based on the current values of the stack, you can ask the caller of your subroutine to pass in how many times they want the loop to run. For example, they could write 10 space count, and we could implement the current subroutine like so. This way, count will count up to whatever number is specified by the caller. Recursion in Forth is done with the word recurse. If you try to write the name of the current subroutine, Forth will get confused. So you write recurse instead. This infinite subroutine will print hello to the terminal indefinitely. Although don't try this in Replit because it will completely lock up your browser. In Swift Forth, it will actually do it. It just won't stop until you type Ctrl+C. Here's a more practical example that counts down from a given number. First, it prints the number. Dupe is used to preserve the number despite it being consumed by the dot operator. Then it decrements the number by 1. Then it checks to see if the number is greater than 0. Again, dupe is used to preserve the number despite being consumed by the comparison operator. Finally, if the previous check was truthy, which will be -1, then we recurse, which means we call the countdown subroutine again in a nested fashion. Now, pay attention as we watch how this recursive countdown subroutine works step by step, with the starting value of 3 put on the stack. It's time for the challenge. I have written up 3 warm-up exercises followed by 1 grand challenge. Challenge number 1. Write 2 subroutines. Say odd and say even. Say odd prints the word odd to the screen. and say even prints the word even to the screen. Challenge 2. Write a subroutine say odd or even. This subroutine takes a number from the stack. It prints that number, and then if the number is odd, it calls say odd. Otherwise, it calls say even. Challenge number 3. Write a subroutine say odd or even up to. This subroutine takes a number from the stack, counts from 1 up to that number, and for each number encountered, it calls say odd or even. Finally, for the grand challenge. The grand challenge is to implement the Fibonacci subroutine. The Fibonacci sequence, if you haven't seen it, is a sequence of numbers that starts with 1 and 1. But starting the third number of the sequence, we can calculate its value as the sum of the previous two numbers. This subroutine takes a number I from the stack and replaces it with the number at the ith position in the Fibonacci sequence. You're worried that you might not be able to solve the challenge. First of all, even if you don't get a working answer, it's not a failure. Just trying to solve the problem will help you learn better when you're learning the solution later. I will present my solution in about a week. Secondly, my son said this to me about overcoming challenges. He said, "When I encounter something challenging, I think more deeply about the problem, starting from what I know." The thing I take away from his comment is, you're not as helpless as you think. Take your time to get your brain going, and you start making progress. I have all these challenges written up in a GitHub repo, and I will link them in the description. You may join our Discord channel if you want to chat with me or others who are working on these challenges.